Okay, well, welcome to another class, another episode, physics series. All right, we're still on optics. All right, it's been an interesting journey so far, looking at optics. All right, and its applications. But today we are looking at another application of optics. Let's proceed to the question. So the near point of the patient's eye is 50 centimeters. The near point. What power must a corrective lens have to enable the eye to see clearly an object that is 25 centimeters away? Now, quickly, how do we solve this kind of question? So the near point is just the distance, the closest distance to the eye, okay? The near point of a person. So the near point of the patient's eye is 50 centimeters. That is our V. What does V stand for in optics? That is the image distance. Right? The image the person can see is 50 centimeters. Okay? Now, what power in diopters? Diopters is the SI unit for power. Must the corrective lens have to enable the eye to see clearly an object 25 centimeters away? So our U, which is our object distance, is 25 centimeters. Don't forget, the formula for the power of a lens or power of a mirror is 1 over the focal length of the mirror. The power of the lens of a mirror is 1 over f. But we cannot get 1 over f until we apply the mirror formula or the mirror equation, which is also the lens equation. And that is 1 over u plus 1 over v equals 1 over f. So we have to get our f first of all. Then after getting our f, we can now put it here and then get our power. Quickly, let's go on. Now, so we have 1 over 25 plus 1 over 50 equals 1 over f. Now take note. The near point of the patient's eye is 50, right? Closest distance the person can see is 50, alright? And we are told that we need a lens, alright? That means the person has a defect, alright? An eye defect. So we need a lens to help the person to see an object 25 cm away. Now, first of all, what case is this? This is a case of long-sightedness. Why? The person can see 50 cm. That's the capacity the person can see. 50 can see a distance, an image of an object placed at a distance of 50 centimeters. But now we need the person to see 25 cm away. So we still need the image to be formed in front of the lens of the eye, okay? Because of that, it means that the image will be negative. Because in the lens diagram, if the image of the object is still formed in front of the lens where the object was positioned, it means that that image will be a virtual image. And for a virtual image, the V is negative. So that means we're going to have a negative V. Okay? So this case is a case of long-sightedness. I told us in the last class, a long-sighted person can see far, 50 cm, okay? But cannot see objects that are close, 25 cm. So let's say we're going to have 1 over 25 minus 1 over 50 equals to 1 over f. Right, our LCM is 50. 50 divided 25 is 2. Okay, 2 times 1, 2. 50 divided 50, 1. 1 times 1, we have 1, which is equal to what? 1 over f. So what do we have? We have 1 over 50 equals to 1 over f. If I cross multiply, f times 1 is f equals to 50 centimeters. So the focal length of this, the corrective lens, the focal length is what? 50 centimeters. Alright? Now, at the beginning, I ought to have converted from cm to meters, but I can still do it here, okay? So if I convert this to meters, that is 50 over 100, and that is 0.5 meters. So therefore, the power of the lens is 1 over f, and that is 1 over 0.5. And the power, this should give us, use a calculator, this should give us 2 diopters. Because 1 over 0.5 is the same thing as saying 10 over 5, and that will give us to diopter. So that is the power of the corrective lens. And if you ask us, what lens are we talking about here? We're talking about a convex lens or a converging lens that is needed to cure the eye defect of long-sightedness. Please like and share this video and follow me for more videos on optics. Thank you.